In this example, we want to solve the system 3x plus 4y equals 8 and 6x minus 3y equals 9. We will choose either substitution or elimination, but we'll notice first off that the graph has been given. The reason the graph was given in this particular example is that you'll notice the intersection point falls somewhere in the first quadrant, but it does not fall evenly on the grid. This is the primary reason we do not rely upon graphing as a method to use to solve every system of linear equations that we come across. In this particular example, I can see that the x-coordinate is a little bit less than 2, and the y-coordinate is a little bit less than 1. But the problem is I don't know what the exact coordinates are, and that's what we need to use. While I am able to use either substitution or elimination, my preference is typically to use the elimination method. So we'll begin by taking both equations that were originally given, 3x plus 4y equals 8, and 6x minus 3y equals 9, and we'll choose what it is that we want to eliminate. I notice that the x terms have coefficients that have a relationship. It is easy to make 3 become 6 simply by multiplying it by 2. What I actually want to do, though, is to remind myself I don't want to turn it into the same value, I want to turn it into the opposite. So I'm going to multiply both sides of this equation by negative 2. In doing so, it will turn that first equation into negative 6x minus 8y equals negative 16. We'll leave the bottom equation untouched, and so it will stay 6x minus 3y equals 9. Before we do the addition step to eliminate one of the variables, we should always verify that they will actually eliminate. 6x and a negative 6x will add to make 0, so we do have the effect that we want. So when we add these together, the x terms cancel, negative 8y minus 3y is negative 11y, and negative 16 plus 9 is a negative 7. And so that gives us a new version of this system, negative 11y equals negative 7. Dividing both sides by a negative 11 will leave me with y equals 7 over 11. Looking back at the graph, 7 over 11 does seem like it would be a little bit less than 1, so that seems like an appropriate y value based on the graph we were given. To finish solving the system, though, we do need to find the x-coordinate. One option is to substitute that y-coordinate back into one of the several green or purple equations that we have up on the screen. What I don't particularly like about that approach is that I'm not in the mood to substitute a fraction of 7/11 into one of those equations and try to solve for the other variable. I can do it, but I'd rather not work with that fraction in the middle of an equation. So our other option, instead of substituting, is to go back to the original system. 3x plus 4y equals 8, and 6x minus 3y equals 9. And instead of choosing to eliminate the x's, which was maybe easier, we can turn our attention to the y's. I look at the coefficients on the y's and I see a 4 and a negative 3, and I know a common multiple of 4 and 3 is 12. So I will choose to multiply the top equation by 3, turning that into a 12y on that equation. And on the bottom equation, I will multiply everything on both sides by 4, turning that coefficient into a negative 12. So across the top, making sure we distribute 3 to everything on both sides, we'll end up with 9x plus 12y equals 24. In the bottom equation, multiplying the 4 across both sides, distributing, we will get 24x minus 12y equals 36. Again, before we add, we are going to verify that those y's will actually cancel out. A 12y minus 12y will cancel to make 0. So now we will go ahead and add the two equations together. 9x plus 24x is 33x. 24 plus 36 gives us 60. Dividing both sides by 33, we end up with x equals 60 over 33. We do always want to make sure that we reduce our fractions. If we cancel out a factor of 3 from both the 60 and the 33, we'll be left with 20 over 11. 20 over 11, I would not normally write this as a mixed number, but as a mixed number would be 1 and 9/11. We'll notice 1 and 9/11 is just a little bit shy of 2, and that does seem to visually verify with approximately where that intersection had occurred on the x-axis. So a quick visual check shows that our two values seem reasonable. We could do a more thorough check by substituting them back into both equations and actually verifying arithmetically that we do get two true statements. But I'm confident with the work that we've done and with the graph giving us that quick visual check that we do have the correct solution. So we'll simply finish off with the final statement. The solution is x coordinate of 20 over 11, comma y coordinate 7 over 11.